This lecture is going to look at section 2.6 out of the book on the Leontief input-output model. We're also going to reach back and take a look at some of the ideas in section 1.10 out of the book, but this is going to be a section that focuses more on some of the practical applications of what you've seen so far with linear algebra. First, we're going to look at something called the Leontief input-output model. Now, this model actually won a Nobel Prize for economics. It is the basis of a lot of economic studies that are still done today. And it is all based on linear algebra principles that we have seen up to this point. So here's the general idea. The general idea is that you have an economy. So for instance, you have the economy of Canada, the economy of Prince Edward Island, the economy of Europe, whatever you define the economy as. You divide it up into sectors. So you have sectors like farming, fishing, manufacturing, tourism, technology, whatever sectors make sense for that economy. So there's a bit of an art in dividing it up into sectors that make sense. But once you do that, the observation is that when these sectors produce things, you want to export them to make money. But out of that economy, you can't export everything. So for instance, in Prince Edward Island, you produce farming products, the products from farming, food. Some of it is internal, some of it is external. So the idea is to figure out how much of it is being used internally and how much externally. So how much is used for internal consumption and how much is a surplus that you can then sell outside. So the Leontief input-output model determines the surplus that you make, or you can think of it the other way, that if you have a certain demand you want to make, how much do you actually produce, knowing that not everything you produce is going to be used or is going to be available for export. Some of it has to be used internally. So let's look at this kind of diagrammatically. For instance, let's say we have an economy that has four sectors: farming, forestry, manufacturing, and technology. So this could be a city, could be a province, it could be a region, whatever. But the idea is here that you have broken up the economy into four sectors, and this describes all the economic activity going on in that region. The idea is that when the farmers produce things, not all of it can be exported. Some section of it has to go to the forestry industry, so they can make the forestry products. Some of the farming product has to go to the manufacturing industry, so they can make their products. Some of it has to go to the technology. And on top of that, some of it has to go internally to farming. So the farmers themselves need to use some farming products. So when all is said and done, at the end of the day, you can't export everything. What you can export is this part, the excess part that you don't need internally. So now this gets a little bit complicated when you look at every one of these industries. So you have the farming industry, which we already saw. They use some internally, and they have some for their export. But now forestry has the same thing. They have to produce some for all the other industries. They need some for their own use, and they need some that only leaves some of what they produce for export. Same thing for manufacturing and for technology. There's only certain parts of what they produce that they can sell externally. So you can see when you start to look at multiple industries and all the interactions, this gets very complicated. And then what happens if all of a sudden you get more demand for forestry? So you need to ramp up production, but some of it has to go to other industries. How can you meet a demand with all of these interdependencies? This is the essence of the Leontief input-output model, which, as I said, won Nobel Prize, has been used for years and is still being used, and is based on the linear algebra that you've already seen up to this point. So we'll often hear things in the news like, an investment is being made that produces a spin-off 7 times the value of the investment, or things about that if an event is hosted, if we bring in this tournament, it's going to produce $7 million in economic impact. Where do those numbers come from? They come from this model. So an example close to home is this, a study that was produced in 2015 for the impact of the University of Prince Edward Island on the overall economy of Prince Edward Island. This study used these principles of the Leontief input-output model to determine that even though the university spent a certain amount and has a certain amount of money flowing through it, the overall economic impact on the island is much more, and it actually quantified what it was. So for instance, some numbers directly from that study talked about some of the direct expenditures of the university. And it has a direct GDP contribution of the university of $109 million. So this is what the university produces immediately in the economy just by them being here. But then you have another concept of total GDP contribution. And it's kind of how much the economy grows or how much of the economy is directly attributable to University of Prince Edward Island. This is both from, for instance, paying staff. This is from the fact that other industries need to supply the university. So manufacturers or caterers have to come in and provide food to the university. Then there's also the induced economic impacts, things that are more distant. So because the university grows the food industry, the food industry needs to buy more raw materials. So that grows another part of the economy, not directly because they're directly supplying the university, but because they're supplying the people who supply the university. And that was found to be $142 million. So you see there's a difference of 30-some million dollars between what you can directly attribute to the university and the indirect and induced contributions of the university. That difference is calculated using Leontief input-output model. So let's look at a simple example. Let's say we have a town that has a very simple economy, only 2 industries, farming and forestry. Now remember Leontief input-output model asks, how do we divide the output of each sector into internal requirements and external or surplus requirements, things that we have available to sell. And here's how it's normally laid out. So let's say that for farming, every time something is produced for farming, every time a unit is produced, it needs 0.2 units of farming. So in other words, it consumes some of its own product. Also, to produce every unit of farming, we require 0.3 units of forestry products. So you can think about this in terms of every unit requires this amount. So if we produce 10 units of farming products, we need to use 2 units of farming and we need to use 3 units of forestry. So you can see as the farming industry grows, we need to use more and more of what's produced internally, which leaves less for export. Same thing with forestry. So produce every unit of forestry, we need some farming and some of the forestry. So breaking it down, for the farming, this gives the requirements for farming, the proportion that we have to use internally. And for forestry, this gives us the amount of internal forestry products we have to use. So now what we're going to do is we're going to take this and turn it into some mathematical equations that describe it. And we're going to see this is going to turn into some linear equations, and then we're going to solve them. Okay, so the first step is to define your variables. Now I'm going to emphasize this point that this is very important because if you write down what your variables are, it prevents confusion later on. And when it comes to the Leontief input-output model, there's really 2 variables we're interested in. Because remember, we're saying how much production is required and how much surplus does it give us. So we define that variable for each of the sectors. So for this equation, we only had two sectors. So we're going to define x1 is the number of units of farming product produced, the total amount, and x2 is the number of units of forestry product produced, total amount of stuff produced. But of course, we can't sell everything. Some stuff is needed internally. So now we're going to give variables for how much is available as a surplus. We let D1 be the surplus units of farming after you've taken care of all your internal requirements, and D2 is the surplus of forestry products after you've taken care of all your internal requirements. So step 2. Now we're going to build what's called the consumption equations. This is going to say for this industry or for this sector of the economy, what goes to each other sector. So for farming, what happens to the farming? The farming stuff that's produced, some of it goes to farming itself, some of it goes to the forestry industry, and the rest of it is available for export. Well, we have two variables already defined. We have the total amount of farming product produced, that was x1. The surplus is d1, the extra. Now we have to get a handle on what's used internally. And that's where those descriptions in the problem come into play. We said that for farming, if you look back at the description of the problem, we said that to produce 1 unit of product from farming, we require 0.2 units of farming products. So, in other words, the total amount of farming stuff produced, you have to multiply it by 0.2 to get the number of units needed just to support itself. So 0.2 times x1 is the amount of farming products needed to support the farming sector. Well, where else can it go? Some of the farming products go to the forestry sector. How much of that? Our problem said that every unit of forestry products that we produce needs 0.4 units of farming products. So we had a variable for the number of units of forestry produced, that was x2, multiply that by 0.4, and that is the amount of farming products needed for the forestry sector. So now we have our equation. The total amount of farming products produced is the amount that goes to farming, that consumed by farming, the amount consumed by the forestry industry, and the surplus. That covers off all of the farming sector. So now do the same thing for the forestry sector. So for the forestry sector, we have two variables that we've already defined. X2 is the total amount of forestry products produced. D2 is the surplus. But all of that forestry product produced, some of it goes to surplus, some goes to farming, and some goes back into forestry. And our problem told us how to calculate the amount that goes into farming and forestry. Our problem said that every unit of product from farming requires 0.3 units of forestry products. So the number of units of farming product produced was x1. So 0.3 times x1 is the amount of forestry products that's consumed by the farming industry. Our problem also said that every unit of forestry product requires 0.1 units of forestry products. So 0.1 times x2 is the amount of forestry product that is consumed internally, that the forestry sector uses themselves. What's left? Your surplus. So again, we have our equation that the total amount of forestry product produced is what's consumed by the farming industry, what's consumed by the forestry industry itself, and then the surplus that's available for export. Now, when you're building these equations, be very careful. Be methodical in building them. It's quite easy to mix up some of the numbers in the equations. So you have to think about it. Each equation talks about where does it go? Where does the farming industry go? Where does the forestry industry go? Be careful when you're building these equations to make sure you don't mix up some of the numbers. So finally, for step 3, notice what we have. When we pull these equations together, we have a system of linear equations, which, as we've seen, we can rewrite this in terms of vectors and matrices. When we do that, we end up with these equations below. And these vectors and matrices have names. The x1, x2 vector, which is the total production for each sector, is called the production vector. And in these equations, it's normally denoted by the letter P. The surplus, which we call the D1 and D2, that's called the demand vector. And it's normally denoted using the letter D. That's the surplus we have, or the demand we have to meet, depending on what problem the exact problem we're looking for. This matrix in the middle, this matrix essentially describes how much of your economy, how much of each sector is needed for internal usage before you can export anything, before you have any surplus. This is called the technology matrix, or it's also called the consumption matrix. And these equations is often denoted with a capital letter A. So let's take this equation and let's rewrite it a little bit and work with it a little bit, simplify it. So you just take these variables. We can rewrite it as P equals AP plus D. Using the P, we said we call that matrix A. Well, you see that's the P again, and then plus D. Well, P is the same as I times P. So we can rewrite it, I times P equals A times P plus D. So now take the AP over to the other side. We get IP minus AP equals D. Now by the properties of matrix vector multiplication, we can gather up those terms on the left side, and we get I minus A. Now I minus A is just a matrix, times P equals D. So now we have a system of linear equations and a matrix representation of that system of linear equations like we've been doing in the course all up to this point. We have a vector, or a matrix times a vector equals another vector, and we know how to solve that. So if you know what P is, you can calculate D with simple multiplication. If on the other hand you know what D is, you can figure out what P is using the techniques we've seen up to this point. So now here's an example. A typical example that you'd see with this type of problem. So if we have an external demand for 10 units of farming and 8 units of forestry, how much do you actually have to produce to meet that demand? Knowing that some of what you produce is going to be used internally, so you have to produce more than what is being asked for. Well, here we use the equation we just determined, I minus A times P equals D. We know what A is, and we know what D is. So what's I minus A? Well, it's the identity matrix minus our consumption matrix, which gives us this matrix. So now we just need to solve that system of linear equations, and we already know how to do that. So let's solve that. Put it into an augmented matrix. Then once it's in the augmented matrix, well, for this one, I'm going to do a row reduction. First off, I'm just going to multiply everything by 10 just to give me nice whole round numbers to work with. Again, you don't have to do that. It's just kind of nice to have full rounded numbers, whole numbers to work with sometimes. Now we start doing our row reductions to solve. So a couple of row reductions, and we end up with this matrix. We have our leading ones, which means that we have found a solution. So the solution for our production matrix is 61 over 3, 32 over 3, which is approximately 20.3 and 10.7. So this is telling us that to meet the demand of 10 units of farming products and 8 units of forestry products, our production vector means we have to produce 20.3 units of farming products and 10.7 units of forestry products. So we were given a demand. We have to find the production vector. It's solving a system of linear equations the way that we've been seeing in the course up to this point. Now, as I said, this is a very nice idea. It's an idea that won the Nobel Prize in economics. It's being used regularly today. In fact, if you go online to Statistics Canada website, you can find the consumption matrices for the entire Canadian economy. Now, they don't use this exact model. They use something slightly modified where there's kind of something in the middle. It's still using basic linear algebra techniques and linear algebra ideas. As I said, it's slightly more complex, but they define three things: commodities, industries, and demand categories. And if you go online, you can download the matrices for the entire economy and solve problems involving the entire Canadian economy. It also gives kind of a baseline so that anybody who's doing these studies in Canada is using the same numbers across the board. But if you go online, these are numbers from a couple of years ago. They have defined the Canadian economy in terms of 627 commodities, 216 industries, and 136 demand categories, and they've figured out approximately the internal consumption and the interplay between all of these different sectors. So it's quite complex what's on there now, quite large, I should say. The ideas are exactly the ideas that we just saw in the previous example. Okay, so let's step through another example. So this time we have a region that has three principal industries: agriculture, manufacturing, and services. And this list down below is the same type of list that we saw before, saying how much of each unit of production, or what the requirements for each unit of production is of the other sectors of the economy. And the question is going to say, well, if we can produce this much stuff, how much do we have left for export? How much surplus do we have? So now we're going to step through the building the equations for this problem. So step one is to define the variables. So we write down exactly what our variables are for production and surplus. So P1 is the amount of production of our first sector, which was agriculture. P2 is the production of our second sector, which is manufacturing. And P3 is the amount of production of our third sector, which is services. Okay, and then we just need one other set of variables. D1 is the surplus of agriculture. D2 is the surplus of manufacturing. And D3 is the surplus of services. So that's our three variables. So now the next step is to build the consumption equations for each sector. So we're going to start with the first sector, agriculture. So if you look back at our problem, the agriculture, everything that's produced in agriculture can go to three different places. It can go to agriculture itself, to four places. It can go to agriculture itself, it can go to support manufacturing, or it can go to support services, or it can be surplus. So we're going to write the equation for everything we produce in agriculture, P1 was everything we produce in agriculture. Some of it goes to agriculture itself. Some of it goes to manufacturing. Some of it goes to the service industry. And some of it goes to the surplus in agriculture itself. So how much of each? Well, our problem says that every unit of agriculture, P1, requires 0.2 units of agriculture. So 0.2 times the amount of agriculture produced gives us how much has to be used internally in agriculture. Manufacturing. Every unit of manufacturing requires 0.3 units of agriculture products. Third one, every unit of services produced, that's P3, needs 0.1 units of agriculture. So this describes exactly where all of the agriculture goes. To agriculture, to services, to manufacturing, to services, and then what's left over as surplus. So there's our first consumption equation. Now let's go on to our next equation. For manufacturing, the P1, the amount that we use to produce the first, or the total amount of product produced for manufacturing, where does it go? Some of it goes to agriculture. Every unit of agriculture requires 0.2 units of manufacturing. Every unit of manufacturing requires 0.4 units of manufacturing. And every unit of support services requires 0.2 units of manufacturing. And then we have our demand, that's P2. Then we have the surplus. So there's our second consumption equation. Now our third consumption equation, using the total production of services, well, some of it goes to agriculture, 0.1 unit of services for every unit of agriculture, 0.1 unit of services for every unit of manufacturing, 0.3 units of services for every unit of services, and then we have our demand, or our surplus. So there's our three consumption equations for the three sectors of the economy. Now we're on to step 3. We write the model as a vector matrix equation. And you remember when we figured out how we do this, we got that P equals AP plus D. And this just gives us our consumption equations in a matrix vector form. So what do we have? We have P1, P2, P3, our production vector, is equal to our consumption vector. Now we get this from our equations. Our first consumption equation had 0.2, 0.3, and 0.1. Our second consumption equation was 0.2, 0.4, and 0.2. Our third consumption equation was 0.1, 0.1, and 0.3. That multiplied by P1, P2, P3, plus our demand vector, D1, D2, and D3. So there is the representation of our economy using the vectors and the numbers we have. But then remember, we took this and we simplified it down to I minus A times P equals D. So what's this? I minus A is our identity matrix minus our consumption matrix that's 0.1 times our production matrix is equal to our demand matrix, or our surplus. So now let's take this and solve it out. Take the first part, the identity matrix minus our consumption matrix. We take I minus A, we get 0.8, negative 0.3, negative 0.1, negative 0.2, 0.6, negative 0.2, and we get negative 0.1, negative 0.1, and 0.7 times our production matrix equals our demand, or our surplus. So there is the theoretical matrix that represents the economy that lets you solve things. Now, what about the specific problem? If you go back and you look at the problem, it said, here's our production. What do we have extra to sell? So we take our I minus A matrix. And once we have this, what do we know? We know what our production is because we're told our production was 2 units of agriculture, 3 units of manufacturing, and 2 units of services. And that equals what we're looking for. We are looking for, after we do all the internal consumption, what's left over to sell? What's our surplus? And when you take these and multiply them out, what you come up with, you will end up with 0.5, 1, and 0.9 as our surplus, what we actually have to sell. So you can see over half of the agriculture is just consumed internally. 2/3 of the manufacturing is consumed internally, and a little over half of the services is consumed internally. So that leaves just a little bit to sell outside. So that's a typical problem with solving Leontief input-output problems. So now let's take a look at our equations again. Recall that we figured out that the equation for our model is I minus A times P equals D. Well, sometimes you will want to solve problems where you have to calculate the required production to meet a demand over and over and over again. And we know that to solve that, we have a matrix times an unknown vector equals a vector that we know. Solving that requires a fair amount of work. Solving a system of linear equations, going through all the row operations, and working out what your vector P is. Well, if you just rearrange this equation a little bit, remember I minus A is just a matrix. So using the ideas that we've seen before, if we can get the inverse of that matrix, we can rewrite this equation in this way. P is equal to I minus A inverse times our demand. And it's much easier to multiply a matrix and a vector than it is to solve a system of linear equations. So here's a key idea that we're going to see here and in other places. That if you need to solve systems of linear equations over and over again where your coefficients are the same, it's usually easier to calculate the inverse and then just do a simple multiplication to get your answer. So, for example, if we have an input-output model that has a certain consumption matrix, and here I give you the consumption matrix, here's a two-part problem. What production is needed if demand is 12.8? And what if the demand jumps? So what if our second sector, all of a sudden, the demand doubles to 16? How do you have to change your production to meet that demand? Well, if you were to solve this out for each of those demand matrices, you would have to solve a system of linear equations twice. And as I said, that's very expensive. I mean, in this case, it's only 2 by 2, but imagine if you had hundreds of equations, it would be very expensive to do it. So instead, what we do is we find our I minus A. So I minus A in this case gives us this second matrix. And we know we're going to have to solve for I minus A times an unknown equals unknown demand. So instead of solving that system of linear equations multiple times, let's get the inverse. So how do we get the inverse? Well, here is our I minus A. We augment it with the identity matrix. Because remember earlier we saw that if you have your matrix and you want to get the inverse, you do your row reductions, then you apply the same exact row reductions to the identity matrix. Well, let's do it all in one here. So we're going to take it, we're going to do some row reductions, and at the end we are going to have the identity matrix on the left, and on the right hand side, that's the inverse. Now that we have the inverse, calculating the production required to meet these two demand vectors is a lot easier because it's just a simple multiplication. So now we know that inverse. If our demand is 12.8, our initial production, or our initial demand, well, our production is 17/16/5. But now what happens if suddenly we get a big new order and the demand doubles for our second sector industry? Well, we have to produce extra of that, but we also have to produce some extra of the first industry just to keep up, just to meet our internal requirements. What happens? A simple matrix multiplication shows us what the difference is. So getting that inverse of I minus A is often used to simplify the calculations to solve the Leontief input-output problem. Okay, so now we're going to look at another type of problem that we can apply linear algebra to get a solution. So we're going to set aside Leontief. We're going to look at what's called difference equations. This is also sometimes called transformation problems. And the idea is that if you have a group of things that you can divide into sets that are non-overlapping, so you have different groups and you know how things change between the groups. This is the type of problem that we can apply linear algebra to. So here's an example. Population. Say we have a city and some people live in the core of the city, some people live in the suburbs. So in this city, we have people in these two different groups. They don't overlap at any one time, but we know that every year some people move back and forth. Now, this is a very simple model. We're going to say nobody moves in or out of this city, okay? Everybody just stays in the city. Nobody's born, nobody dies. It's a very simple representation of this type of problem. But let's say that every year in this city, 15% of the people in the core of the city move to the suburbs, and 10% of people in the suburbs move into the core of the city every year. So in 2020, so that we have 500,000 people who live in the core of the city, 400,000 in the suburbs. What does it look like next year? What does it look like in 2021? What is it the year before in 2019? How does it change? And again, we're going to use linear algebra to solve this problem. Again, it's very simple. We don't have any other changes in population. So just a bit of a graphical, diagrammatical representation. We have people who live in the core of the city. We have people in the suburbs in a given year. So we started this one in 2020. Every year we have some changes. So over the next year, we have, of the people who are in the city, what happens to them? Well, we're told that 15% move to the suburbs. So that means that 85% stay in the core. What about suburbs? We're told that 10% move into the core of the city. So that leaves 90% to stay in the suburbs. So for the next year, 2022, what happens? Same thing, 85% and 15%. And of the suburbs, 10% go back into the city, and 90% stay in the suburbs. And this keeps going on and on and on. So we have a state and we have transitions, how things change from year to year or from time to time. So again, we are going to start the first step with define the variables. Again, I can't encourage you enough to write out what your variables are for any of these problems. We're going to say let C, where the subscript is the year, be the number of city dwellers in a given year, and S, with a subscript of the year, be the number of suburban dwellers in a given year. So we were told in the problem that in the year 2020, we have 500,000 people in the core of the city and 400,000 in the suburbs. So we're going to simplify by saying 500 and 400, where it represents the thousands of people living in the city or the suburbs. So step 2 is again determine the equations that describe the changes. So we're going to look at one of these groups at a time. So in this case, we're going to say the city. So the core of the city. CT is the population a given year. How does it change as we go to the next year? So how does it change as we go from C 2020 to C 2021? And now remember we had our little diagram. We had 2020 and 2021 with the city and the suburb. And remember what happened. We had in the city, we had 85% stay in the city core, 15% go to the suburbs. From the suburbs, we had 10% go to the city core and 90% stay in the suburbs. So we know what 2020 is. What we're asking now is what happens here to the city in 2021. So if we look at what comes in, well, how do you describe that entire group? Well, it's 85% of the people who were in the city core beforehand. And it's 10% of the people who are in the suburbs. So that means that CT plus 1, in this case CT through to 2021, is 80% of the people who were in the city core the year before, and 10% of the people who were in the suburbs the year before. Now what about the suburbs in the year 2021? Well, the suburbs in that year, what makes up that? 15% of the people who were in the city core and 90% of the people who were in the suburbs. And that totally describes the population based on the previous year. So now we have two equations. We have how do you get the city and the suburbs from the year before? So we can write these as vector matrix equations. So C of t plus 1 and S of t plus 1, we have the equations for it based on the previous year. Rewrite it in vector matrix equation. We have 2021 is equal to a matrix times what happened in 2020. This matrix is often called a transition matrix. It describes how things change from one year to the next or one state to the next. It's not always time. In this case, it's from one year to the next. So now we go back to our problem. We know what the status was in the year 2020. How do we get 2021? Well, to get 2021, that's the year t plus 1, the next year, we take our transition matrix, multiply it by what we know, what happened in 2020, and we get the population in 2021. So in the year 2021, we have 465,000 city residents and 435 suburban residents. But now remember our problem had two questions. It said, what's it going to be in 2021? It also said, if we know what it is in 2020, what was it in 2019? What was the previous population? Well, we can also figure this out. So we have that our population in 2020, so C 2020 and S 2020, is equal to our transition matrix times what it was the year before. So C 2019 and S 2019. And we know what C 2020 and S 2020 is. That was 500 and 400. So again, look at what we have here. We have a matrix times an unknown equals a known vector. That's a system of linear equations that you know how to solve using Gaussian method or row reducing. You're building the augmented matrix and row reducing your matrix. So you can go ahead and solve this. And you can solve it in one of two ways. You can either take the equation that you have here, use the augmented matrix and solve it out, or you can look at your matrix the way that we did for the earlier example, find the inverse of it, because remember this is A times C of 2019, or your 2019 matrix is equal to your numbers for 2020. Well, you can flip it around and say your 2019 numbers is equal to A inverse times your 2020 numbers. And then it's a matrix multiplication once you find the inverse. Once you have that inverse, then you can use that to easily calculate what happened in 2019, what happened in 2018, what happened in 2017, and so on. You can start to reach back into the past. And you can do it a lot easier than solving that system of linear equations for every single year. So here in today's lecture, we've seen a couple of places where the linear algebra that you've seen up to this point is used to really influence things that happen today. The Leontief input-output model is heavily used in economic theory even today. The transition or transformation problems are used quite a bit in biology and other sciences and in a lot of other areas to describe how things change from one year to the next or from one state to the next. These are a couple of very important models that use exactly things that you've seen in this course up to this point.